Okay, so let's get going here. You guys should be able to see my screen here in a second. Is that working? You can see my screen now? Okay, good. All right, so we left off last week. We left off talking about solving absolute value equations. Okay, and so what did we say? Well, we came up with some ideas. Idea was to isolate the absolute value first. So we're going to think of the absolute value as being just one thing. You can almost think about it as like even making a variable substitution. You don't have to write it down, but in your head, you're thinking about it that right. It's just one big thing that we need to isolate, right? So we've got 4 times this absolute value, and don't even worry about what's inside at this point. Absolute value of something, call it u, minus 2 equals 38. Well, we know what the steps would be to isolate something. If I'm trying to isolate the absolute value, I'm just reversing order of operations and using inverse operations. So I'm just going to add 2 to both sides, I'm going to divide by 4, and then I end up with my isolated absolute value just equals 10, right? The absolute value of something, call it u, is equal to 10. Well, then what values could whatever's inside, call it u, what could u be? If the absolute value of u is 10, well, u could either be negative 10 or positive 10, right? Okay, but it's not a u. I mean, it was something. It was something involving x's. We made this substitution. Now let's go ahead and get rid of these. And the point is, we just haven't, whoops, that's not right. I want that one. There we go. We just haven't really focused on what's inside, but once we isolate the absolute value, whatever inside is either going to be set equal to negative 10 or positive 10, and then we're just going to solve those 2 equations individually, right? No big deal, okay? So we're going to get 2 answers to this. X is equal to 2 or X is equal to negative 8, okay? All right, and will those, well, will those both work? How would we know if both of those worked? What would we do with our answers? Substitute it back in. Yeah, we could just plug it back into the original, couldn't we, to see that they both work, okay? And they would. They would in this case. Okay, so what does this tell us then? Let's look at this in terms of a graph. So we know that if the absolute value of u is equal to a, well, let's graph the absolute value of u. The absolute value of u is just going to be a V-shaped graph, as we talked about last Thursday, right? And if that's equal to a, if this graph is equal to a, it'd be like saying, okay, well, then the output of this function, the y value equals a. So I could draw a horizontal line up here that the line y equals a is this line that I've drawn, right? And we're looking for the intersection of that horizontal line with the graph of the absolute value function. Well, it's happening in 2 places, isn't it? If this is the line y equals a, and this is the absolute value function is just a function with a slope of 1 on the right side and a negative 1 on the left leg, then would you guys agree that the coordinates of the intersection, I'm going to have to go over as far as I go up because this slope is 1. And so if the y value is a, right, then what did I graph there? Did I say 8? Well, that's supposed to be an A, not an 8. What am I doing? Right? This is the line y equals a, right? Because we want to know when does the y value equal a. So then if the y value is a and the slope is 1, doesn't the x value also have to be a, right? So the coordinates of that point are over a and up a. And what about this one over here? Well, if the y value is a and this slope is negative 1, that's going to have to be a negative a, isn't it? Right? And so that's kind of a graphical way of representing why we get the results we do, right? We know that if I'm going to map these down to the x-axis and I want to know where are the solutions to this, well, the solutions are going to be at u equals a or u equals negative a, right? We're just looking for only the x coordinates in this case, right? We're not asking about the y values. The y value is a, but we want to know where is that true? Well, it's true there and there. And that's why we get those two separate solutions, right? Either u equals negative a or u equals positive a. Thumbs up, thumbs down, thumbs sideways. How are we doing on that? Okay, good. All right, so let's just do, today's just a review day. It's not going to be, we'll get into some newer stuff here soon, but this is all going to be pretty much review, I think. So try this one. Just really quickly on your scratch paper, try this one on your own. Solve that equation.
So on our notes,
Mm-hmm.
in the warm-up for the absolute value page,
Mm-hmm.
number 2 says the absolute value of x is equal to negative 4.
Okay, right. So we're going to look at one like, your question is, how can that happen, right?
Yeah.
Okay, yeah, hold that thought. That's a very good question. We'll talk about one like that here real soon. Very, very good question. Yep. Okay, so what are the steps here then? What are we going to do first? Abby, what'd you do?
I first subtracted 11 from 79.
Perfect.
Both sides.
Good. Okay, so we subtract 11. Very good. So those cancel. So I get 2 times my absolute value of, who cares, right? We're not even looking inside. We're just trying to isolate the absolute value, equals 68. And then Miss Tesh, what did you do next? Okay, good. Divided by 2. Very good. Okay, and so we isolated our absolute value, the absolute value of something. What is it? Well, okay, it turns out it's a 2x minus 20. So the absolute value of 2x minus 20 is equal to 34 when I divide by 2. And so what 2 equations is that going to give me, Mr. Demanu?
Right. 2x minus 20 equals 34, and then 2x minus 20 equals negative 34.
Okay. So now I want to be very precise on this. What is the symbol that has to go, Andrew? What symbol do I have to put in the middle? Is that going to be an and or an or?
Or.
It's going to be an or. Good. They can't both be true, can they? That's an or statement. So there are my 2 statements. And then I would just solve those. So when all the dust settled, what do we get for our answers on this one? Chloe, what'd you get? We subtracted 20 and divided by 2, and what'd you get? Oh, you added 20 and divided by 2.
X equals 32.
Yeah.
And,
Okay.
yeah, x equals negative 7.
X equals negative 7. I'm buying that. This one, that doesn't seem right to me. If I'm...
sorry. I can't add. 4. So that would be 27.
Good. Right. And you guys can probably do those in your head, can't you? I mean, we're going to add 20 at 54, divide by 2, and get 27. Good. Okay. So those are our 2 solutions we should get, 27 and negative 7. Good. And if we plug those both in, do they both work? Let's just try it. So if I try 27, 2 times 27 is 54, minus 20 is 34. Absolute value of 34 is 34, times 2 is 68, plus 11 is 79. Check. What about negative 7? 2 times negative 7 is negative 14, minus 20 would be negative 34. Absolute value makes it positive 34, so it's going to work, right? It's the same math from there on out. Okay, good. Good. Okay, what about this guy? So I'm going to get rid of this. So we've got an absolute value of something, but we don't care what, because we can't do algebra inside the absolute value. What's our first step going to be here, Dawson? Yeah, good. Good. We're going to isolate the absolute value by multiplying each side by 3. So the 3's cancel. Very good. And then we get our isolated absolute value is equal to 156. And inside we've got, it looks like 4x minus 20. So let's see. Now, gosh, can you help me out with your name? How do I say that? Delube. Okay, good. I wasn't sure, but that's a cool name. That's a cool name. That's good. So what am I going to do? Delubed. I said that right, correct? What am I going to do? What are my two equations I'm going to set up then?
4x minus 20 equals 156.
Okay.
And then 4x minus 20 equals 1 negative.
Okay, and what do I have to say in between? Or, good. So 4x minus 20 equals 156, or 4x minus 20 equals negative 156. And so what do we get? Who got an answer for that? If we solve those, what do we get? X equals 44, or X equals negative 34. Is that what everybody got? Give me a thumbs up if that's what everybody got. Okay, good. And we could check those, and they're going to work, I'm assuming. I'm not going to take time to check them this time. Okay, what about this one? This is a little strange. What are the two steps in order to isolate the absolute value here, Jace?
I don't.
So I'm just trying to isolate the. So what that means then, isolate the absolute value, and let's get rid of. We'll get rid of that guy, right? But the part that we're trying to isolate, is just right here. So think about that just like a variable. We're just trying to get that by itself. How am I going to get that red blob by itself? What are the two algebra steps to isolate it?
You add 11.
Okay. And then
Divide by 2. But
good. Okay, but something weird is happening, isn't it? Yeah. Okay. Right. So when we add 11 to both sides, look what happens here. I end up with 2 times the absolute value is equal to 0, right? So if you divide by 2, what's 0 divided by 2? 0. Okay. So I'm not getting two equations out of this, am I? This is an instance where there is no 0 is neither positive nor negative, right? And so I'm only getting a single solution out. What do you think that corresponds to in terms of the intersection of my absolute value function with 0? Where is the intersection occurring? If I go back a couple slides here to this picture, the blue line has moved. We're not asking where the absolute value equals some positive number. We're asking where it equals 0. And so where does the intersection occur? There aren't two of them this time, are there? Right? If I slide that blue line down, what are the coordinates of the intersection? Anybody help me out?
0, 0.
0, 0. Yeah, look. If I slide this blue line down, these points are migrating together, aren't they? These points are migrating together, and they're bumping into each other and becoming a single point at the origin, aren't they? Yeah. Okay, so we're only getting, and it makes sense that we're only getting a single answer this time. The answer is just going to be whatever's inside is equal to 0, right? There is no opposite of 0. And so if I subtract 6 and divide by 3, what do I get for my single answer? -2. And if I plug it in, that's going to work. 3 times -2 is -6 plus 6 is 0. Absolute value of 0 is 0. 2 times 0 is 0. So I just get -11 equals -11. It does work, but there's only one solution there, isn't there? Okay. All right. So what about this one? Maria, what's going to happen here? If I try to isolate the absolute value this time, what's going to happen?
The number it's equal to is going to be negative.
Yes. Look, we're going to add 1, right? And we're going to divide by 3, and that's going to give us I'm going to get 3 times my absolute value equals -6. I'll divide each side through by 3, and I'll get my isolated absolute value is equal to -2. Well, what's inside is a 2x minus 1. What can you guys tell me about that?
How can an absolute value equal a negative number?
That's my question to you, can it? It can't, can it? Look, that would be like asking, if we go back to our graph, that would be like asking where's the intersection of the absolute value v and a line that is below the x-axis, right? There is no intersection, right? And so what do we say about that? If there's no intersection, then what can we say about the solutions or lack thereof? What do you think?
No solution?
Yeah, there's no solution, is there? It's impossible. You can't have an output of an absolute value that's negative. Whoops. Okay, and so there's nothing, I mean, and sometimes people make a mistake. They go on with this and say, okay, well, look, what's inside, we get two equations. What's inside, 2x minus 1 is either going to equal -2, or what's inside is going to equal its opposite, which is +2. And I could solve those equations, but I'm going to get nonsense answers. They're not going to make sense. That'd give me 2x equals -1. So then either x equals -1/2, or what about over here? If I add 1, I'm going to get 3, and then divide by 2, x equals 3/2. Let's check them in the original equation and see if they work. In the original equation up here, here's my original equation, right? If I plug in 3/2, what am I going to get? I'm going to get 3 times the absolute value of 2 times 3/2 is 3. So that's going to be 3 minus 1 is 2. Absolute value of 2 is 2. So I'm just going to get 3 times 2 minus 1 equals -7. Well, that's not true, is it? So that one fails. What if I try the -1/2? I'm going to get 3 times -1/2 times 2 is -1. -1 minus 1 is -2. The absolute value makes it positive, and so I have the same problem. They don't work, do they, if I plug them back in? Okay, so that's one where, yes, our answer should be no solution. And I would tell you that you ought to be able to see that right from the beginning. We ought to be able to see it right from this, at least from here, right? If we have an absolute value set equal to a negative number, we know immediately that's going to be no solution because the output of an absolute value function cannot be negative. Okay? Thumbs up, thumbs sideways, thumbs down. How we doing? Good? All right. Okay, what about one like this? I've got an absolute value of, who cares, we're not looking inside yet, is equal to 4x plus 4. What am I going to do here? Kendall, any ideas? Caught you mid-yawn.
I don't know yet.
Okay. That's tricky. It's got a variable in it. Anybody have an idea?
Could you distribute like a negative throughout it? So the one would be positive 14x plus 4 equals absolute value, and then the other one would be negative 14x minus 4.
Yeah, good. We're just going to follow our rules, aren't we? We're going to say that whatever's inside, call it u, right, equals either positive 14x plus 4 or whatever's inside equals negative 14x plus 4, right? Well, what's inside? Let's take a look. What's inside is a 12x minus 14. So we get the two equations, either 12x minus 14 equals 14x plus 4, or 12x minus 14 equals, if I distribute the negative, I get negative 14x minus 4, right? I'm just going to solve both of those. Let's see. We could, where are we pushing the x's here? To the right, it looks like, right? We'll subtract 12x, which means we'll push the numbers the other way. So I'm going to get 2x equals negative 18. You guys correct me if I'm wrong here. So I get x equals negative 9 as one solution. Everybody agree? Thumbs up. Did I do it right? Okay. Or what about over here? I'm going to push, this time I'm going to push the x's over this way, aren't I? Push the numbers that way. So I'm adding 14x, which is going to give me 26x. I'm adding 14. So 26x equals positive 10. Divide by 26. X equals 10 over 26, which is what? 5/13. So there's my other solution. X equals negative 9 or x equals 5/13. How could I know if they're right? Plug them back in. Okay, let's use technology. Let's use technology to do that. So here's a great application of Desmos. Desmos makes this easy. I can't remember if I've showed you this yet or not, but either way, I want to show it to you again. So we'll pull up Desmos graphing, and we're just going to set, when I want to see if something works in an equation, I'm just going to evaluate both sides of the equation for that answer and see if I get the same number on both sides, right? Does that make sense? I'm going to plug negative 9 into the left and the right and see if it gives me the same answer. Agreed? So in Desmos, an easy way to do that is to use function notation. Let's set f of x equal to what's on the left side of the equation, which is the absolute value. Well, I guess I can't do that. I go like, there we go, like that. So the shortcut for absolute value in Desmos, you can always go down to here to the, where is that? Boy, this has changed. Oh, that's not Desmos at all. That's my recording. What the heck? Where's the toolbar in Desmos? There is a toolbar here. Like if I go, I think it's just hidden behind this thing. It is. I'm pretty sure it is. Hide tools. There we go. Oh, here it is. Yep, there it was. Okay. I can show the keyboard, and inside the keyboard, I've got functions. So I could do like all those different functions. I could do stats functions. I can do distribution stuff. I can do miscellaneous. And where's my absolute value? Why am I missing absolute value? Oh, there it is right there. Well, I didn't even have to go to the functions. It's right there. Everybody see that? So I can just type that button and it's going to open up absolute value bars for me to type in. Okay, there is a shortcut though. So let's get rid of those keyboard shortcuts. The shortcut is, it's good to know this stuff. You're going to use Desmos a lot. The shortcut is the button right above enter, where it's got the backslash. Right above the backslash, you see either a vertical line or it looks like two vertical dashes, depending on your keyboard. If you hit shift and type that button, that's your shortcut for absolute value. I tell you that because we're going to be doing a lot of stuff here in the near future with absolute value stuff. And so you're going to want to know where that is. So I've got the absolute value then of what's on the left side, which is 12x minus 14. We got to be inside the absolute value. Whoops. 12x minus 14. It gives me a graph. I don't really care about the graph for this, honestly. I'm going to set up another function. Let's call it g of x. It has to be a different function for the right side, which is 14x minus 4. Okay. And I just want to evaluate these things. So one of my answers is negative 9. So I'm going to do f of negative 9 gives me 122. If I do g of negative 9, what better I get for my answer? What do you think I'm going to get?
Hopefully 122, right?
122, okay? If negative 9 is an answer. It didn't work. So what's that tell you?
That's wrong.
It's that negative 9 is not a solution. We did the algebra correctly, though, right? We did the algebra correctly. Negative 9 was an algebraic answer, but it's what we call an extraneous solution. So we have to always, here's the moral of the story. When we've got variables on both sides like this, when we're setting up multiple equations, we must always check our solutions because it's possible that we're going to get some extraneous solutions. Let's try the other one. What was the other one? It was 5/13. Okay, so let's try that one and see if we have better luck. 5 divided by 13 gives us some bizarre decimal. If I put it in here, notice, oh, what happened? What happened? So they're both extraneous. Is that right? Oh, you know what I did? Oh, look what I did. I typed in the wrong. That's supposed to be a 14x plus 4, isn't it? Not minus 4. Okay, so these both worked. Okay, maybe the other ones did too. Let's try them. They didn't though. Everybody see that? Okay, so the negative 9 did not work. It gave me positive 122 in the first equation, and it gave me negative 122 in the second one. And if I were being clever about this, I should have known right away that negative 9 wasn't going to work. How come? Everybody tell me, just looking at those equations, why you could be guaranteed that one's not going to work.
Because you would make the absolute value equal to a negative 9.
Exactly, because that would have made the output of the absolute value negative, right? So that one had to be an extraneous solution. Okay, did everybody? That was kind of with my mistake, sort of obscured that a little bit. But did everybody see how I used Desmos on this to evaluate it? That's pretty handy to do, and you're free to do that. Okay. All right, so that was an important result. We found that when we checked it, that's a non-solution. That's extraneous. but this was a valid solution. So we got the single solution, x equals 5/13. Questions? Thumbs up, thumbs down, thumbs sideways. Okay. All right. Okay, so I thought, how are we doing for time here? I thought with you guys, we're going a little faster than normal. I thought maybe we would just charge ahead and look at graphing inequalities too, and just review that. Graphing inequalities using interval notation and then solving inequalities. And this is straight review. I mean, this is going to easy stuff, but I want to make sure we at least talk about it briefly. So when we're graphing inequalities, let's fill in some blanks here. We use if we're talking about a greater than or equal to or a less than or equal to symbols, what kind of a dot, what kind of an endpoint are we going to use for our graphs? As opposed to if we're using just a plain old greater than or less than, if we're not including the equals. If we, okay, good. So it's going to be solid, right? If we're including the equal signs, it's solid. It's going to be open. If we're not including the equal sign, right? Make sense? Interval notation. Okay, so interval notation is an alternative to using inequalities, right? With interval notation, we're going to use a combination of infinity symbols, parentheses, and brackets. Okay, so parentheses indicate not included or open, right? So those are what would correspond to inequality symbols without the equal sign included. Brackets indicate included or closed, and solid, that's really, closed is really the math word we want for that, right? Instead of solid. And so that would be what we would utilize if we had an endpoint of an interval that included equal signs, right? So let's do a couple things here. Let's just take some simple examples, and let's first of all graph. How would I graph x is greater than or equal to 8? Well, here's a number line. I'm gonna make this 8 and that 9 and that 7. So how would I graph that? On the number line, how do I graph x is greater than or equal to 8?
Put a circle on 8 and fill it in.
Okay, so we got a solid endpoint, and then I'm going
to point the arrow towards the 9.
Good. So we're going up to infinity, aren't we? We're taking all values greater than 8, so we're going to shade to the right. If a is less than -1, I'm going to make that -1, so that's 0, and that's -2. What kind of endpoint am I using? Solid or open? Or closed or open?
Open.
Open. And this time I'm just shading to the left, aren't I? Right? Okay, how would we write those with interval notation then? So with interval notation, we're saying all values greater than or equal to 8. So our interval has to always start with in this case, it's starting with the endpoint because it's going to the right. Okay, so we're going to open up, we're going to have a bracket, and we're going to include the 8, right? That means that our lower limit, whenever we use interval notation, it's always going to follow this pattern. The interval notation, whether they're parentheses or brackets, this is going to be the lower boundary, right? Or the lower, I'll call it that, lower boundary. And this is going to be the upper boundary of our interval. Well, in this case, the lower boundary of the shaded interval up here is 8, right? And I put brackets because I am including the 8. It's a closed endpoint, which means we are including that value. It goes forever to the right. So how could I assign a number up here to the right that means it goes forever?
Infinity.
Infinity. Yeah, and it's not really a number, is it? But it's the idea that there's no limit on this thing. I'm going to put infinity. So what this tells me is that I start at 8 and I rise to infinity, which means I just go forever. I'm going to increase towards infinity. I never get there. Okay, here's an important question though. What kind of symbol do I need with the infinity? Do I need a bracket or do I need a parenthesis? What do you think? I can see justifications for both, but there's definitely a right answer here.
Would it be parentheses because it's open?
It's open, right? So they are parentheses. It's gonna look like this. That is the correct answer. What's my justification for that though? Why couldn't I put a bracket on the infinity? A bracket means I would be including infinity.
Is it because it's not really a number?
Yeah, you can't include infinity because infinity is not a number, right? If I put a bracket on that, it would mean that there is some endpoint to the right, and there is not, right? It just goes on forever and ever. That's why we must, whenever we're using an infinity, we must use a rounded symbol on that to indicate that it's an open interval on that side. So this is what we'd call a semi-closed interval. It's closed on the left, but it's not closed on the right. Okay? How about this one then? Interval notation. So now this time I've got my comma, which separates my lower boundary or my left boundary from my upper boundary, which is my right boundary. Where does the -1 go this time? To the left of the comma or the right of the comma?
The right.
It's got to be the right, doesn't it? Because this one has a top limit, but not a bottom limit. So we've got our -1, parentheses or brackets to the right.
Parentheses.
Yeah, because we're not including the -1. Well, what would I put on the left then to indicate that the interval goes forever in the negative direction?
Infinity.
But what kind of infinity?
Negative.
Negative infinity, exactly. It's got to be a negative infinity. Because on our number line, on the real line, this is the positive direction. So that's going towards positive infinity. And this is the negative direction. So that's going towards negative infinity, right? Okay, makes sense? Okay, so what about down here? So solving inequalities. We're going to follow the same rules when we're solving inequalities, the very same rules that we follow when we solve a regular equation with a couple of exceptions, right? And we're only going to really talk about maybe one exception for now. Follow the same rules to solve an inequality you do with an equation, except what do we have to do to the inequality symbols when we multiply or divide by a negative number?
Can you flip them?
Yes. That's the only thing we have to really remember. Otherwise, the algebra is the same for inequalities that it is for equations, with that one exception for now. There'll be some other exceptions we'll add later, but for now, that's all we need. Okay. All right. So let's just quickly see if we can crank through one or two of these. Are we out of here at 40 or 45? 45. Good. So we'll have plenty of time. Yeah. Okay, so what are we going to do here? Talk to me about this one. I've got an inequality that involves some variables and some distribution and stuff. How do I treat this?
Simplify.
Just going to, good. Okay, we're going to simplify first, aren't we? We're going to treat this just like an equation, which means we have to simplify until we have a single variable we can point to. So we're going to work our way down the order of operations tree like normal until we have a single variable we can point to. And then we'll use inverse operations. All right, so what do we have to do to simplify? If we work our way down, there's nothing inside parentheses we can do, so we can skip through that step. There are no exponents. Is there any multiplication? Yes, there is multiplication, absolutely. Pagan, you're nodding your head. Where do you see multiplication?
There's a 3 outside of the parentheses.
Okay, good. Good. So we'll distribute that -3, won't we? Did I say your name right?
Yeah, you did.
Okay, perfect. All right. So if I distribute the -3, we get 21x, minus 15x minus 27 is greater than or equal to 7. So we had some multiplication. Looks like there's some addition there. What's the addition look like? Somebody? Rebecca, would you? Either Rebecca, I don't care.
The 21x minus 15x.
Okay, good. So that's going to combine to 6x minus 27 is greater than or equal to 7. Good. And now we bottomed out, didn't we? We got to where we can point to a single x. And so now we can use inverse operations and isolate the x. Sarah, what are the 2 steps in order to get the x by itself?
You have to add 27 to both sides and then divide both sides by 6.
Okay, good. So we end up with, if we add 27, we're going to get 6x is greater than or equal to 34, right? We divide by 6. Now I'm dividing by a positive, so do I have to flip the inequality? No, just regular. Okay, we divide by 6, and we get x is greater than or equal to 34/6, which would be what, 17/3? Right? So if we were going to graph that, what would that look like? So that's going to be 5 2/3. So what if I made this 5 and that's 6 and that's 7? So 5 2/3 is roughly there, right? Open or closed endpoint? Closed. Shading to the right or the left?
Right.
Good. So there's my graph. If I want to use interval notation then, somebody walk me through exactly what that's going to look like then. Natalie, what am I going to write down? What's the first symbol I write if I'm going to write this using interval notation?
A bracket.
Bracket. Good. Then what?
17/3.
Good. That's my lower boundary. Very good. And then now what?
Then infinity.
Okay, and then comma, and then infinity. Good. And then what kind of enclosure do I use? Parentheses or brackets? Yeah, good. Everybody see that? Good stuff. Okay. Good. Okay, let me see. I want to just see what. Let's do this. I'm gonna skip up to this one. That's all right. We'll do this one first. We may not get through everything today, but we'll get a lot of it out of the way for next time. So what do I have to do here first, everybody? What's the first item of business? Simplify. So that means I'm going to go ahead and I got to multiply first, right? I'll distribute the negative, which is like multiplying by -1. So I'm going to get 3 minus 4m minus 1, right, is greater than or equal to 5m minus 25. Now we have a choice at this point. We could either push the m's to the left and have a negative number of variables, or I could push the variable to the right. Which one do you think is probably preferable? I'm seeing a lot of people pointing to the right. Yeah, it'd be to the right, wouldn't it? Does that make sense? We want to go to the right because then I'm not going to have to worry about whether or not I have to flip the signs. I know I don't have to. So we're going to push the variables to the right. While we're at it, let's go ahead and push the numbers to the left. So that's going that way. This guy's going to go this way then, right? And we end up with, what about the variables? 5m plus 4m is 9m. Here I've got 3 minus 1 is 2, plus 25 is 27. Last step. I'm seeing people are saying it. Divide by positive 9, which means I don't have to flip the sign, and I get m is less than or equal to 3. Now that looks kind of backwards, doesn't it? Right? So how would we probably want to rewrite that? We'd like to have the variable first. Everybody see that if I'm going to flip that around, 3 is greater than or equal to m is the same thing as saying m is less than or equal to 3. So that's our answer. Okay. All right. Time to go. I will, real quick, I've got we're going to use Math Excel for School for our math assignments now. We purchased the licenses. We'll get it set up. Next time we meet, we'll get it rolling. Okay, I'll have a class built for you. So I may or may not even put up any more assignments on the Google Forms. They're just a pain to make and they're not very good. So I think we'll probably just hold off and I'll give you 2 assignments next time. Does that sound good? Excellent. All right, go to class. Have a great day. I'll see you in a couple days. Okay, so we were talking, last time we met, we were talking about inequalities. We were just kind of pushing through some review. And we reviewed interval notation, and we started solving some inequalities, right? And I think we left off with something like this. Okay, yeah, let's do this one. Solve the inequality. So what do we have to do here? What are we going to do? We're going to have to do some distributing, aren't we? We have to simplify each side first so we can distribute the 4. If I distribute that 4, I'm going to get, correct me if I'm wrong, 48x plus 16 is greater than 48x minus 160, right? Give me a thumbs up if I did that correctly. No mistakes? Good. All right. Now what? Next step would be to push the x's to one side or the other, right? And you're right. You could have divided both sides by 4 first. That would have been a good idea. Sure. It would have made things a little easier, wouldn't it? Okay. What about now? What do we need to do next? I mean, where am I going to push the x's here? I'm kind of, this is a weird situation, isn't it? I can't push the x's to either side. When I subtract 48x from both sides, look what happens. The x's cancel, and I'm left with the statement 16 is greater than negative 160. How do I interpret that?
The inequality is correct.
The inequality is correct, yeah. But we're trying to solve for x here, right? That's the whole point, is we want to find the values of x that satisfy the inequality, that make it true. So what does that mean? If we end up with the x's dropping out and we have a true inequality, how do we interpret that?
Like all real numbers.
That's it. That's exactly right. So if, just like with equations, if the variables drop away when we're solving an inequality and we're left with a true inequality, that implies that all real numbers are solutions. How would I write that using interval notation? How do I write all reals? We talked about interval notation the other day, right? We talked about how we can express, we can express intervals with inequalities or with interval notation, right? Remember that solid bracket implies a closed endpoint, an open bracket implies an open endpoint, or a rounded bracket, like parentheses imply an open bracket. And we always organize our interval notation with a comma in the middle, the lower boundaries on the left and the upper boundaries on the right. Well, how would I do something like all real numbers then? So I know right away that I'm going to have a comma with my lower boundary and my upper boundary. But if it's all real numbers, what's my lower boundary?
Is it negative infinity?
Yes, it is. So on the left, my lower boundary is negative infinity, meaning there is none. What about the right?
Normal infinity.
Okay, so positive infinity. And then the only issue is, what kind of, do I need parentheses or brackets? Has to be parentheses, doesn't it? And we talked about that last time, because brackets would say something that's nonsense. That would imply that we're including these numbers, but they're not numbers, are they? Right? To think about the concept of infinity, it's a difficult thing to do. There's one exercise that I always do in class that I think helps people with this a little bit, is the idea when you're talking about sets that are infinite. Like we talked earlier about the fact that there are an infinite number of rational numbers between 0 and 1, right? That's a weird thing to think about. But imagine that I'm standing facing the door to my classroom. Okay, and here's the game I'm going to play. Every second for the rest of eternity, I am going to cut my distance to the door in half. So you have to kind of, you can't really see me doing that right now. So you're going to have to just sort of visualize that. It's not hard to do though, right? Every second, I'm going to cut my distance to the door in half. Do I ever get to the door? I never get there, do I? Right? Now, here's the weird thing though. I never get there, but if I had, you know how when you buy Sharpies, you can buy the chisel point or the thick point or the really fine point on the Sharpie. Well, let's say I had a Sharpie that had an infinitely fine point. Is there any point I could make on the ground between me and the door that I wouldn't eventually step on or over? In other words, could I make a point on the ground that I'd never get to? If the point has to be between me and the door, it can't be on the door, right? It has to be on the floor between me and the door. Is there a point I could make on the floor that I would never get to? What do you think? Give me thumbs up if you say yes, thumbs down if you say no. That's a weird one, isn't it? Okay, the answer is there is no point that I couldn't get to, right? And what you might be thinking, this is a difficult concept. We'll start talking about this now, and in calculus, we'll talk about it a lot more. But what you might be thinking is, well, just pick the point next to the door, right? If I pick the point next to the door, I could never get to that one because I can't get to the door. Maybe that's your logic. But if I think that I've picked the point next to the door, I'm wrong, because how many points are still between me and the door? You get my point?
Yeah,
It's infinite, right? All I have to do is just keep zooming in more and more and more, right? If I think I'm at the point next to the door, I can just zoom in more and find an infinity of points that are still there between me and the door, right? So that's the way math works. Now, it is worth mentioning that in modern physics, the really recent developments in physics lead us to believe that it's probably not the way the universe works, that it's entirely possible that there is some minimum length in the universe called the Planck length, which is like 10 to the minus 46 meters. And physicists are starting to surmise that once you get down to that scale, there is no longer such a thing as distance. You can't get any smaller than that. So in this sense, math is separate from the universe in some important ways. We use math to represent it, like my background's in physics. And so everything we do in physics, we build mathematical models to describe the universe. But there are still places where math just diverges from the universe. It's an interesting topic. Okay. But I digress. Let's get back on track here. So here's how we would say all real numbers. Okay. What about something like this guy here? Let's see. Yeah. What about this one? Okay. I have to simplify, right? I'm trying to solve the inequality, so I'm going to isolate x. There is no single x that I can point to, so I have to simplify. What would I do first? Somebody just click on a mic here. Let's try to get through this quickly.
You could like put the negative number into the parentheses?
Okay, good. I'll distribute the negative, won't I? Same thing as distributing a -1. So I'm going to get 6x minus 4 is less than or equal to 3x minus 12 plus 3x, right? And if I combine like terms, I'm going to get 6x minus 4 is less than or equal to 3x, and 3x gives me 6x minus 12. Once again, look what's going to happen. When I subtract 6x from both sides, the 6x's cancel, don't they? And you can just show your work by canceling the 6x's. That's fine. So then what do I get? I get the result -4 is less than or equal to -12. How do I interpret that? Is that true or false?
False.
Okay.
Yeah, so there's no solution.
No solution. Yeah. So how would we say that using, say, interval notation? Well, there's a bunch of ways in math that we can say there's no solution. The solution set contains no element. So one way we can do it is to signify the empty set. Okay. Okay, compound inequalities. I'm sure you guys are familiar with compound inequalities. What does the word compound mean?
Multiple or human?
Yeah, multiple, right. So we're going to combine multiple things in one here, aren't we? Right? Let's see something here. Whoops. There we go. Hang on one sec. Okay. Just want to make sure I'm filling in the same stuff that shows up on your notes. Okay, here we go. So what is compound inequalities? That just means multiple together, right? So compound inequalities, really that's just saying two or more inequalities taken together. So we might be graphing them on the same number line. We might be expressing the solution set to both of those at the same time. So there's two types. There's an or type inequality, and for an honors class like this, I'm going to give you the name for that. So that's called a disjunctive inequality. And an or inequality is always written with the word or. So for example, if I wanted to represent this graph as an inequality, this is an or inequality because the regions that are graphed are separate, right? They're distinct from one another. If you think about an ant crawling along the number line, would you agree that an ant can't simultaneously be on this part of the graph and that part of the graph, unless it's a quantum mechanical ant, but we'll talk about that later. Okay. So how would I say this? Like, what about, let's color code this. So here's the red part of the graph. How would I say that part? X is what?
Equal to or less than -4.
Okay, so less than or equal to -4. What about this part of the graph, the blue part? X is what?
X equals greater than
X is
-1.
looks like +1. X is greater than +1. And because those are separate intervals, I have to connect those with an or. Now, our symbol for or in math is just like a capital V. Okay, that's our mathematical symbol for or. So if I wanted to use interval notation on this, then, this is just going to be, well, look, we have the graph here, which is kind of nice, isn't it? So the red interval The upper limit is going to be -4. What's the lower limit for the red interval?
Negative infinity.
Negative infinity. Good. And I'd have to have a bracket, correct? Because that's a closed endpoint. And here I have to have parentheses. And then my or statement, I'm going to write that as I can either write it as a V, or the other thing we could do in math. This literally means, and I want to make sure you guys understand this. So in math, that literally means or. If I write a capital U like this means the union in math. Union means we're going to combine everything. The union of something means we're going to take everything together, okay, all of it together. So we could either use an or symbol, or sometimes when we're using interval notation, people will talk about using a union symbol, meaning it's going to be the combination of this part and this part. We'll take them both, even though they're separate intervals. Just like the graph, we're going to consider both of those intervals as part of our set, okay? So, and then the blue side would just be open parentheses 1 to infinity, right? Okay. Okay, so when we're solving OR inequalities, it's really simple. You guys probably remember this. You just solve them separately, right? They're literally separate inequalities, and we'll just work down. Like, imagine there's a line separating the two, and we're just going to go through the steps for solving for x. Well, what are the two steps in order to solve for x here? You guys can do this in your head.
Subtract the 4 and divide 3.
Okay, what am I going to get if I do that? If I subtract 4 first and divide by 3? 2. And I don't flip the sign because I didn't multiply or divide by a negative. So there's part of my solution. And then over here, all I have to do is divide by 5, right? So I'm going to get x is less than or equal to 2, or is greater than 5, right? Everybody agree? And if I were to graph that using interval notation, or graph it and then write it using interval notation, I'm going to get less than or equal to 2, solid endpoint at 2, graph to the left, or x is greater than 5, I'm going to have an open endpoint at 5, graphed to the right. And so this guy here in interval notation is going to look like closed bracket, open parentheses, negative infinity, comma 2. The union of that with the interval where 5 greater than 5. So we'll have parentheses, 5 comma infinity, right? Make sense?
Divided by 5 is not 5.
Oh, you're right. It's 9. What am I doing? Thank you. Yeah. So that's got to be a 9. I got to fix this, don't I? Whoops. So that should be like that. There we go. There. How about that? Is that better? Is that fixed? Give me a thumbs up if that looks like that's correct. Okay, good. Thank you. Okay, let's look at this one real quick. We got another OR inequality. What are the steps to isolate x for our first inequality? What do I do first?
Multiply by -3.
Okay, now if I multiply by a negative, what do I have to remember to do? Flip the sign. Okay, good. So that's going to give me, if I do that, if I multiply each side through by -3, that's going to give me the -3's cancel, and I get 8 minus x. Over here, -3 times -5 is +15. I have to remember to flip that sign. And then what about now?
Add the 8 subtract the 8 and then divide by -1.
Okay, I could subtract the 8. If I subtract the 8, I'm going to get -x is greater than or equal to 7, right? And then if I multiply or divide by -1, I'm going to flip the sign, right? So I end up getting x, That becomes a -7. And I've got to flip this guy again, flip it back. So there's my answer for the first part of my OR statement, right? Now, incidentally, this is fine to do it this way. We could subtract 8 and multiply by -1. The other thing we could have done here, I just want to show this to you, because this is another way to go with this. The other thing we could do is we could add the x to this side. So I end up with 8 equals x plus 15, subtract the 15 to get my -7. That's not supposed to be equals. It's supposed to be greater than or equal to, like that, right? And then now all I have to do is just turn this statement around so the x is on the left. Either way, I'm going to get the same answer, aren't I? Right? You pick. And then over here, we've got this other inequality we have to deal with. What are the steps there in order? On this side? Got to isolate that x. Okay, we could do that first if we want to. So let me rewrite this. If I distribute a 2 through everything, that makes life a little bit better, doesn't it? That's going to give me 10 minus 3x is less than -2. Good. And now, last two steps.
-10 from both sides.
Okay, subtract 10. So I get -3x is less than -12. Divide by -3, right? Which means I've got to flip my sign around. And so there's my final solution. X is less than or equal to -7, or x is greater than 4. Okay, and we could graph that. That's no big deal to graph. So less than or equal to -7 looks like that. Greater than 4 looks like that. If I want to write that using interval notation, everybody agree this looks good, right? Got to have brackets on that one. Or I can use my union symbol. You can use the V here also. I mean, they're essentially interchangeable. At least for now, we'll think of them as being interchangeable. The V and the U, or union. Okay, does that look good? Thumbs up if I'm good. Okay. Okay, type 2 is an and inequality. Okay, so and inequalities, these are called conjunctive inequalities. And so how would we say this? Okay, if we want to write it out using words, we would use the word and, right? So we would say, you tell me, how would I say that then? I'm trying to describe here, how do I say that interval using the word and?
X is greater than or equal to -2, and x is less than 5.
Perfect. Yeah, you always want to you want to kind of start in the middle here in a sense, right? You want to define it's greater than or equal to what low, or greater than or greater than or equal to, depending on the problem. It's greater than what lower limit and less than what upper limit. So that's exactly right. We would say x is greater than or equal to -2, and our symbol for and is an upside down V, and x is less than 5. Okay, using interval notation, how would I do this one, do you think? Well, I have to have a comma in the middle. What's my lower boundary?
-2.
-2. What's my upper boundary?
5.
Good. And then I need a bracket there, right? Because that's closed. Parentheses there because that's open, right? Okay, so when we rewrite these, though, the and falls between the two endpoints, but really that's a clumsy way to say it, right? If we said something like, for example, let's look at this top one we did right here, right? If we did something like x is greater than or equal to -2 and x is less than 5, well, why don't we write that instead this way? Greater than or equal to -2 and less than 5. See how much better that works? When we have and, compound and inequalities, conjunctive inequalities. Oh boy, this pen is really not writing very well. It's like it's running out of virtual ink. Conjunctive inequalities. We always want to compress those into a single statement. Okay, it's much, and there's a reason for that. Doesn't this match the graph better? Doesn't that work better? Because the x is in the middle, we can see that the -2 is the lower limit, the +5 is the upper limit, and I'm including that equal sign there, which fills in the endpoint, right? Way better way to do it, okay? So we want to always condense these. The other thing that's nice about this is when we solve compound and inequalities, rather than having to break it into separate inequalities, we can deal with everything all at once, which condenses the algebra a little bit. Okay, let's look at an example. So what about this one? First of all, can we rewrite this? I mean, we could just go down and solve both of these separately, but could we go ahead and just, well, actually, no, on this one we can't. Sorry, that's bad. I'm thinking of a different problem. This one, we just have to solve these two separately, okay? So we're going to put our line down the middle. And what are the steps to isolate x in this inequality?
And subtract 3 from -9.
And then divide by 2. So what do I get? X is greater than?
-6.
Okay. How about over here? Add 2, divide by 8. What's that going to give us?
16. No. 4.
4. There you go. Or and x is greater than 4. Now we have to have an and statement there. Okay, so can I write this? Can I condense this into one compound and inequality, first of all? Let's put the x in the middle. How am I going to write that? X is always going to be greater than the lower boundary and less than the upper boundary, right? So x is going to be greater than -6, right? And less than +4. Everybody see that?
You didn't divide by a negative. Why did you switch the sign on the second?
Oh, I didn't mean to. Thank you. Didn't mean to. It's supposed to be less than. Darn it. Good thing you guys are watching me. I'm making mistakes today. Right? So that's the lower limit. X is greater than -6. The upper limit is x is less than +4. Right? Does that make sense? That's how we'd combine them then into a single compound inequality. And if we wanted to graph that, we're just going to go from -6 up to +4. And I've got open endpoints on both sides. Using interval notation, of course, that's just going to look like that. Okay, questions? Good? All right. So what if we start off with a compound inequality that's written in compressed form, right? It's written as, this is a compound and inequality. It means two things, right? It means 3p plus 4 is greater than 4 and less than 19. So how do I do the algebra here? Well, all I have to do is just treat all three parts of this compound inequality the same. So I'm going to subtract 4, agreed, first. And what's that give me? The 4s will cancel, so I'm going to get a 3p in the middle, I'm going to get a 0, and I'm going to get a 15, and I did not multiply or divide by a negative, so I do not flip my inequalities. Last step is I divide by 3. So the 3's cancel, and look what happens. I get p by itself, I get 0, and I get 5, and I don't flip anything. So there's my final answer. Okay, if I graph that, I'm just going from 0 up to 5. In interval notation, it just matches the graph, doesn't it? It just looks like that. Okay, we good? Thumbs up? Okay. What about this one? A little more to do here, right? So to isolate that x, would everybody agree the first thing I'm going to do is multiply everything by -2? So what's that going to give me? If I multiply by -2, that's going to give me a +10. It's going to cancel the -2 in the middle. And here I'm going to get a +4. But what do I have to remember to do?
Flip all the signs.
Flip the signs. I multiplied by a negative. So everything is going to get flipped around, right? And then what now?
Subtract 12.
Subtract 12. Okay, so we end up with -2. Those cancel. I get a -x and a -8. And then last step.
Multiply by -1.
Yeah, multiply by -1 to change the sign. So then that becomes positive, that becomes positive, that becomes positive, and I have to flip, right? So there's my solution. Okay. So if I graph that, it's just going to look like that, right? So using interval notation, whoops, I already made a mistake. Using interval notation, that becomes a 2, that becomes an 8, that's a bracket, and those are parentheses. Okay, I want to get through one more here. Oops. Okay, I'm going to make one up. I want to show you one more thing. Okay, what if I have something like this? What if I can make it easy. So we do -4. I've got -2x and 8. Simple inequality to solve, right? I'm just going to divide by -2. If I divide by -2, this is going to become a +2. That's going to become an x. That's going to become a -4. Of course, I'm going to flip the inequality symbols around. Can I leave my answer like that? Or does that look a little funky?
It looks kind of funky because don't you want the least one to be on the left?
You do. Exactly. Yeah, you do. We want this to match. If I were to graph this thing, we know what the graph's going to look like, right? X is greater than -4, right? So we know that that's going to be our lower limit, and X is less than 2. So we know that the graph would look like that, wouldn't it, right? Well, when we write a compound inequality, we want the compound inequality to match the graph. So what do we have to do? We have to take this whole thing and just flip it around. So imagine that this is written on a glass slide using pen or something, right? All I'm going to do is take that glass slide and just twist it around so the x stays in the middle, the -4 ends up there, and the 2 ends up there. Well, what does that do? It means that this relationship, x is greater than -4, now fits there, and this relationship, x is greater or is less than 2, fits there. So what if I had done something, let me just make one little tweak to this to make a point. What if that had been a less than or equal to? So that became a greater than or equal to. Then, let's see. Then that would have showed up here, wouldn't it? See what I'm saying? 2 ends up being, x ends up being less than or equal to 2. Well, the 2's got to be on the top. So that symbol ends up there when I flip it around. You get my point? I didn't articulate that very well, but I think you guys all understand what I'm saying. Okay, last issue, and then are we out of here in 1 minute? Yep. Okay, so one last thing here. What does this mean then? These union and intersection symbols. So this means union. If I flip it around, it means intersection. Okay. So this literally is saying the intersection of these two sets. Okay, well, let's think about this in terms of a graph for a second. I think we're out of time. We'll do this now. We'll wrap up this last little part next time. There's only a couple questions on the assignment about it. So you guys can jump into the assignment, get going on that, and I will see you day after tomorrow.